So more questions from waves. First, I prefer like now complete this topic and then we move to another one. Every session we'll try to do the classified papers. So you will have a better understanding of the topic. And from January onward, I will start the regular test, the topic wise test. The last we did was page 40. The last we did was page 12, page 30. Progressive wave y passes at a point P. The variation with the time for the displacement of x and for the P is shown. Look, one thing, when they show or give you a progressive wave and they ask, draw an arrow to show the motion of the particles. This is not in the question, but I'm just giving an idea. If they said, like example, there's a progressive wave. Progressive wave means moving wave, like the wave travel or move from one place to another. And this progressive wave is given, and they say, draw an arrow to show the direction of the motion of particle, let's say A, B, and C. Okay. So how you will represent in a progressive wave? Progressive wave means moving wave. So how you represent the motion of the particle of a progressive wave? So what you will do, you will just sketch the new position of the wave, just draw the same wave, same time period or same wavelength, but in a new position, dotted lines. And now as you can see, A, what will the new position of A? So A will be up. What is the new position of a B? B will be up. And what is the new position of a C? C will also be up. The position of the particle. They ask like which direction the particles are moving in a progressive wave. So what is the rule of knowing the direction of the motion of the particle of in the progressive wave? So we just roughly sketch a new position of the wave ahead of the first one, which is given to us. And the new position of, because the particle A was here, but new position of A is this. Particle B was here, new position of a B is here. Particle C will be here. So means A, B, C, and are moving up here. But what if the question was standing wave is given to you and they say draw an arrow to show the direction of the motion of particles? So if a standing wave is given to us, and the particle is there, let's say particle A is there, particle B is at the center, and particle C. So particle A is here, and if this was a standing wave, so in a standing wave, the particle move towards the mean position. So if A is there, A will move towards the mean position. This was C, C will move towards the. What about B? B is at the node, so B will not move up or down. That is the motion of the particle in a standing wave. So, and the particles on the adjacent sides of node are always 180 out of phase. Like if one particle is going down, the other particle will go up. So particle A and C are actually 180 out of phase. And that is also a characteristic of an standing wave, that the two particles which are on adjacent sides of the node are always 180 out of phase. If one is going up, another one will goes down. So if they said, like example, particle P is here, and this is a progressive wave. So if I want to show the direction of this particle in a progressive wave, so how it can be done? I will just sketch the new wave. New position of the wave. So this is P, so now this is the new position of P, so P will be down. If this was, let's say B was there, this is the new position of a B, so means B will move up. If this was C, this is the new position of a C, so C will move down for a progressive wave. Now the question that the progressive wave y is passing at a point P The variation with the time to the displacement x for a p is shown. The wave has a wavelength of 8 centimeter. Determine the speed of the wave. So if you want to determine the speed of a wave, we already have the time period. As you can see, one complete crescent trough, that is a time period. So t is 0.4 seconds. The wavelength is there 8 centimeter or 0.08 meters. So speed is frequency times the wavelength. But we don't know the frequency, but the frequency is reciprocal of the time period. So we can take 1 over t. So we can say 1 over 0.4 times the wavelength, that is 0.08. What's the answer? 0.08 divided by 0.4. So it will be 0.2 meters per second. So 0.2 meters per second. A second wave Z has a wavelength of 8 centimeter and amplitude 2 millimeter. The wave Y and Z have the same speed. For the wave at point P, calculate the ratio. So we want to calculate a ratio of their intensities. We know amplitude intensity is directly proportional to the amplitude square. Or we can say amplitude intensity divided by amplitude square will always be a constant value, K. So the intensity of Y divided by the amplitude of Y. What is amplitude of Y? The distance here, which is in millimeter, 4. What about the other? That is also 2 millimeter. So this is 4. So we can say 4 square is equals to K. Then intensity of the Z divided by its amplitude square, 2 square is equals to K. But the ratio between the intensity and amplitude square will be constant for the two waves moving at the same speeds or interfere. So it will be, we need the ratio of intensity of Z over Y. So if we compare them, the intensity of a Y over 4 square, which is 16, intensity of a Z over 2 square is 4. We cross multiply, so 4 over 16 is equals to intensity of Z divided by intensity of Y. 4 over 16 is 1 by 4. So the ratio is 1 is to 4. IZ over IY. Or you can also say 0.24. 0.25. Is it clear? The ratio of the intensities of the two waves. In page 14, describe the condition that for a two waves to able to form a stationary wave. Again, a same repeated question, that the condition for formation of a stationary wave, that the two waves must move in opposite direction. Two same type of wave. Same type of a wave must move in opposite direction, should have the same speed and frequency on the wavelength for interfere. So must move in opposite direction and should be same type of the wave, and they should have the same frequency or the wavelength. No, same type is different, same frequency is different. Like example, you can have a sound wave with a frequency of 20,000 hertz. You can also have a light wave with a frequency of 20,000 hertz. But the sound wave and the light wave cannot interfere with each other. For a stationary wave, the two same type of wave, like nature should be same. If one is sound, the other is also sound. If one is light, the other should also be light. A stationary wave on a string has a node and antinodes. The distance between the node and the antinode is, adjacent node and antinode is 6 centimeter. What is meant by the node? So how we define a node in the standing or a stationary wave? It is a point in a stationary wave where particles are not moving or the amplitude is 0. And what is the wavelength of the two waves forming in a stationary wave? So nodes and antinode distance is 6 centimeter. So the distance between node and antinode is actually quarter of the wavelength. So the quarter of the wavelength is 6 centimeter. If we need the wavelength 6 multiplied by 4, 24, the wavelength of a wave will be 24 centimeter. State a phase difference between the between the particle of two adjacent antinodes. As I mentioned, remember this, when two particles are on adjacent sides of antinode, what is the phase difference between adjacent sides of the node or adjacent sides of antinode? What is the phase difference between them? The phase difference between them is 180. So 180 degrees always the phase difference in a stationary wave. Like we have this antinode and we have this antinode. So if this group of particle will move down, this group of particle will move up. So they're always 180 out of phase because the directions are opposite. Then we have what if the two peaks, what if it was two peak antinode? No, it cannot be, because the idea is that when a stationary wave is formed, we draw a stationary wave like this and we draw a dotted line like this because to show the new position. So either the particles will be in the dotted part or the particle will be in a continuous part. If the particles are in a continuous part of their antinode, this will be the motion. If the particles are on the dotted side of antinode, this will be the motion. So they are always 180 out of phase irrespective of, because either one side will be up, other side will be down. So these two are 180 out of phase, these two are also 180 out of phase. If we take three antinodes, like example, say we took three antinodes, A, B, C, D, or four antinodes. A is going down, B is going up, C is going down, D is going up. But the question is adjacent. So what are the adjacent antinodes? So adjacent antinodes are AB. You can see AB are 180 out of phase. What about BC? BC is also 180 out of phase. What about CD? CD is also 180 out. All the adjacents are 180 out of phase. AC are in phase, but these are the successive, not adjacent. These are called adjacent antinodes. These are successive antinodes on the same side. They will be in phase. There is no phase difference between A and C. A and C are in phase, or we can say 0 degrees. Or you can also say in phase. And A, B are anti-phase or 180 out of phase. The term in phase and anti-phase is used. Then define in terms of energy what is meant by longitudinal wave, the wave in which the particle vibrate parallel to the direction of energy transfer. State the principle of superposition. When the two or more waves will meet at a point, the resulting displacement is a sum of individual displacements. Again, the same. Then we have a diffraction question. A wavelength of a light from a laser is determined using an apparatus. A Young's double slit experiment is there. This is D is given to us. Or you can also say A is given, because when two slits are there, lambda is equals to AX over D. Which is, with this D is this distance. X is the spacing between the two successive fringes, like two successive bright or two successive dark. And A is the spacing between the two slits. In a double slit, if it was a diffraction grating, then we use a formula D sine theta equals n lambda. So this is a double slit. That's why lambda is equals to AX over D. So a light from a laser is incident normally in a plane double slit. A separation between the two slits is, so A is given to us. The screen is parallel to the plane of a double slit. The distance between the screen and the double slit is 2.3. A pattern of a bright and the dark fringe is seen. The separation between the bright fringes is this, so X is given. We want to determine the wavelength in nanometer. So our direct formula lambda is equals to AX over D, where A is spacing between the slits, that is 3.7 exponent minus 4. X is the spacing between the fringes, that is 4.3 into 10 to the power minus 3. And the D is a distance between the screen and the slits, that is 2.3 meter. What's the value for lambda? 692 nanometer. 6.92 exponent minus 7 meter. Yeah, that's right. And if I convert, because the question was give your answer in nanometer. So if I'll give in nanometer, it will be 692 into 10 to the power minus 9 meter or nanometer. 692, it correspond to which color? Which color is this? So it is a red color, because red is having approximately 700 nanometer the wavelength. You have to learn the wavelength of all electromagnetic radiation, the range. Because in exam, they ask this question that identify what is seen, which color is seen, which part of a spectrum it belongs to. So it's important, not frequency. Look, the simple way, just learn the wavelength. And if you need, if they in exam, they ask a frequency, use the formula V is equals to F lambda. You remember the wavelength, you know the speed, they all have the same speed, 3 exponent 8. So you can work out the frequency. So don't memorize both frequency and wavelength. Just memorize the wavelength and then you can convert into frequency. The intensity of a light passing through each slit was initially same. The light through one slit is now reduced. Compare the appearance. We need to know all colors or just read it. All colors you have to learn. Compare the appearance of the fringes before and after the change. Look, they mention the intensity of the radiation is same in the beginning. So when the wave's intensity is related to amplitude, like amplitude is same. When the two waves meet at this point, we'll have a central maxima. Like example, they both have the same intensity. So let's say the dot is it's. So when they combine with each other as a result of a combination, what will happen? This will be the resultant. So we'll observe a maxima here. Okay. Then they meet another point. Crest of one joined with the trough of another. But because they have the same intensities or amplitude, because intensity is intensity proportional to amplitude square. So means they have the same amplitude, but when they meet 180 out of phase, they completely cancel out the effect of each other and will observe a minima, means dark. So there will be a minima and maxima. Maxima means constructive interference and minima means destructive interference. That is what happened when we were using the same intensities. Now in the question they said that one of the slit, the intensity of a light is different from the other and it is reduced. That is what mentioned here. The intensity of the light passing through each slit was initially same, but the intensity of a light through one of the slit is now reduced. So one of the slit they have now reduced. So what will happen when we were observing a maxima here? Say this was 2 centimeter and 2 centimeters. So this amplitude was 4 centimeter. The resultant amplitude was 4 centimeter. But now what happened? One is reduced, like this is say 2 centimeter. And the other one is, let's say 1 centimeter. When they will meet, they will have a constructive interference, but this constructive interference will not have the same intensity. It will be 3 centimeter high compared to the first one, because when both were having the same amplitudes, so when they were combining, the combined wave will be double. But here one is higher amplitude and another one is smaller. So the combined amplitude is smaller than this original one. So when we observe the maxima, maxima means like constructive interference. So the brightness will decrease. The brightness of the maxima will decrease. Is it clear till this point? What happened to the brightness of a maxima or the bright fringe? Is it clear? Should I repeat? No, I'm not saying 4 centimeter, 3 centimeter. I'm just giving you an idea, the concept. I can do it without numbers as well. I can do without number, like when the both were having the same intensities, like this is wave 1 and this is wave 2. So when both were having the same intensity, the resultant wave will be higher. When the same intensity. But now they said one of the intensity is lower than the other. So if the one intensity is lower than the other, they meet constructive interference, but the resultant wave intensity will be lower. So you will have the maxima, but you will have the maxima or the bright fringe, but that bright fringe will have a lower intensity as compared to original one. Same thing, when two waves meet, a destructive interference occur. When they were having the same amplitude, they were completely cancelling out the effect of each other, and you was getting a dark. But now what happened? One is higher and another one we have reduced. So they will cancel out the effect of each other, but you will not observe a dark there. You will observe some light. Why? Because they are not able to completely cancel out. If this was, let's say, 2 centimeter and this is 1 centimeter, so this is still 1 centimeter in height. So when we reduce one of the intensity at the maximum, what will happen? The intensity of the maxima will decrease. And what will happen to minima? The intensity of the minima will, in place of a minima, it will be bright. Because they're not able to completely cancel out the effect of each other. Is it clear, this concept? So the number of the maximas and the minimas will not change. The number of the maximas or minima will not change. Like we'll have a maxima, then we'll have a minima, we'll have a maxima, we'll have a minima, we'll have a maxima, we'll have a minima. But what will happen if the two light rays were the same intensity, when we were using same intensity and they combine with each other? As a result, it will be higher maxima. But now when they combine with each other, one is smaller than the other. So when they combine, the resultant wave will have a lower intensity, lower amplitude, smaller amplitude. So this was bright. This is also bright. But when you compare the brightness before and after, you will observe the brightness of the maxima will decrease because its amplitude has decreased. And what about the minima? When it was forming a minima, like when it is forming a minima, the crest of one was joining with the trough of another, so they completely cancel out each other. So we will have dark here. But now what is happening? The one wave is higher amplitude than the other one. So it is not able to completely cancel out. Some wave is still there. Lower amplitude, but some still wave is there. So it means instead of the minima or the dark fringe, we'll observe the light. So how we write the answer there, we'll mention the brightness of the maxima or the bright fringe will decrease, where in place of a dark fringe, we'll have a bright fringe. Or there will be light, high intensity. Is it clear? So these are some questions from the topic waves. So next week we'll select another topic to do the papers, the classified one. Once we are done with the classified, like 50% of these exercises, remaining you will solve as a practice. Then we'll start the past papers.